Good morning, and welcome to day 4 of our AP Calculus free response question advent calendar. Hope everybody had a great weekend. It's a chilly Monday morning here. I want to remind you to download the document yourself that contains all of the questions that we're doing during this advent calendar. You can find a link to the document in the description and in my pinned comment, so you can work along the questions with me before watching these solutions. Let's get into it, see if we can find slot number 4 in our advent calendar of chocolates, which is not nearly as exciting as an advent calendar of calculus. There it is, here in the top right by the starry sky. Look at that, it's right on the snowy roof of this building. All right, I'm going to crack into this, and I will put the problem we'll be solving today on screen. It is from the BC exam, so you can see it now. We're actually dealing with infinite series today. Should be a lot of fun. We got a red chocolate here. It's so hard to get these spheres out of the compartments. Guess I'll just have to do that again. Pro tip, I guess, for anybody watching, trying to figure out how to extract their chocolates from their advent calendars. Let's see how this is. It's so tiny, but it's so good. Makes me just want, oh man, it's got some chocolate inside that's so good. Just makes me want a bag of like full-sized Lindt truffles. Dang nabbit, that is good. All right, I am ready to do some calculus. This is problem 6 from the 2001 AP Calc BC exam. So this would have been the final question. No graphing calculator allowed. Let's take a look. A function f is defined by f of x equals this power series, where we can see a general nth term given there. This equation, of course, is only true for all x in the interval of convergence of the given power series, so that's the domain. And part A is to find this domain, this interval of convergence for the power series. And of course, we must show the work that leads to our answer. So let's go ahead and get into part A. We're going to use the ratio test. This is what the series in question looks like. The form, of course, was given to us, and we know that n has to start at 0 so that we agree with that first term, because there shouldn't be any x's in that first term, so we need x to the power of 0 for that first term. Now, hopefully you remember the ratio test. The ratio test involves a limit statement, and we take the limit of this expression, the absolute value of the n plus 1th term of the series divided by the nth term of the series. And in this case, that's going to work out pretty well, because 3 to the n plus 2, I say n plus 2 because we're plugging in n plus 1. So 3 to the n plus 2 and 3 to the n plus 1 are going to cancel out fairly nicely, and n plus 2 and n plus 1 will also cancel out as n goes to infinity. We have to take this limit as n goes to infinity, and when we do that, n plus 2 and n plus 1 are barely different, right? They would approach 1. So let's go through the details of evaluating this limit. Again, this is the ratio test, and we don't need our series to have any special properties to apply the ratio test. We can just jump right in to the limit. So for the ratio test, like I said, we're going to take the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. We're going to write that division, though, as multiplication by a reciprocal. Let's begin with the n plus 1th term. So where you see n, we are plugging in n plus 1. So the numerator, n plus 1, is actually going to be n plus 1 plus 1, which is n plus 2. Again, that's because we're replacing n with n plus 1. We also have x to the n plus 1 up here. And then in the denominator, we have 3 to the n plus 1, but we're plugging in n plus 1 for n, so that's 3 to the n plus 2. Then we divide by an. To do that, we'll multiply by the reciprocal. So the stuff in the numerator, n plus 1 and x to the n, will be in the denominator. We have n plus 1 and x to the n. And the denominator, 3 to the n plus 1, because we're multiplying by the reciprocal, that's going to go up to the numerator. Now, we just have to see what needs to be true about x to make this limit less than 1. The ratio test tells us that the series is going to converge so long as this limit equals something less than 1. So we need to see what condition does this force on x, and in order to figure that out, we're just going to have to make some simplifying steps. And there is a lot of simplification we can do here. I just duplicated the limit so we can start crossing stuff out. 3 to the n plus 1 and 3 to the n plus 2 almost completely cancel out. It just leaves one factor of 3 in the denominator. N plus 2 and n plus 1, those cancel out as well. In theory, we could split this up into a product of limits, and when we have just n plus 2 over n plus 1 on its own, well, as n goes to infinity, these two things are virtually identical, and so they would approach 1, and thus they're not actually having an effect on the limit. The x's will also almost cancel out. X to the n plus 1 and x to the n, that's just going to leave a single factor of x in the numerator. And so we have simplified this considerably. At this point, we don't even need the limit statement because we've gotten rid of all of the n's. So we need the absolute value of x over 3 to be less than 1. This means that x over 3 is less than 1 and greater than negative 1. Multiply everything by 3, and we get that negative 3 is less than x is less than positive 3. Now, the ratio test tells us as long as this limit is less than 1, and so all of this has to be true, then our series will converge. But it doesn't tell us anything about the endpoints, so we'll have to check these endpoints separately. We know that our series will converge when x is between negative 3 and 3, but it's possible it also converges at the endpoints. We'll have to check. And here's what happens if we evaluate those endpoints where x is negative 3 and where x is positive 3. In the negative 3 case, this x to the n, of course, becomes negative 3 to the n. The effect that has is almost canceling out with the denominator, just leaving a single factor of 3 in the denominator, and also giving us a negative 1 to the n up in the numerator. This series clearly diverges because it just gets bigger and bigger while flipping from negative to positive. In the case where x is positive 3, this x to the n is just 3 to the n, and so the same thing happens except without that negative 1, and again, this series will diverge because the terms just get bigger and bigger. The terms don't approach 0 in either case, so both of these series will diverge by what is called the divergence test. If the terms of the series don't converge to 0, the series must diverge. And so our final answer for the interval of convergence is from negative 3 to positive 3. Neither of the endpoints are valid points where the series converges, and so that is our final answer for part A. Part B asks us to find the limit of f of x, that's our power series, remember, minus a third all over x as x approaches 0. So let's write out this limit statement. X approaching 0 is within our interval of convergence, right? So this is totally valid. And also notice, as we go to write this, that we are subtracting 1/3. So this 1/3 at the start of our power series, we don't have to worry about that. That's just going to get canceled out with this minus 1/3. And we'll just be left with f of x over x, but without the 1/3. So this is what the limit statement looks like. In the denominator, of course, we have x. In the numerator, we just have our series, excluding that 1/3 at the beginning that canceled out with the minus third. So we just have 2 over 3 squared x plus 3 over 3 cubed x squared, and so on. In each term, the power of x and 3 both increase by 1, and this numerator increases by 1. So what's going to happen is one factor of x in every term will cancel out with the x in the denominator. So let's write that step. So now we're looking at the limit as x approaches 0 of 2 over 3 squared, that factor of x got canceled out, plus 3 over 3 cubed x. It did have an x squared, but one of the x's got canceled out, and so on. Every term of our series just has one less power of x. So since x is approaching 0 in this limit statement, all of these terms that have an x in them are going to go away, which just leaves this first term without the x, which is 2 over 3 squared, and so this limit is equal to 2 over 9. Alright, I just shrank our work and moved it out of the way so we have a little bit more room for part C, which asks us to write the first 3 non-zero terms and the general term. So that's just like they did here, right? They wrote the first 3 non-zero terms of the series and then a term representing a general form. That's what we're supposed to do, right? The first 3 non-zero terms and the general term for an infinite series that represents the integral of this function f of x from 0 to 1. So let's go ahead and set this up. I'm going to write the integral from 0 to 1, and then I'll put our power series in here. So here's what it looks like, the integral of our power series. Now we can go ahead and integrate each individual term, and we'll be evaluating that from 0 to 1. The first term, 1/3, integrates to 1/3 x. The second term, well, we have to increase the power of x by 1, so we would increase it from 1 to 2, and then divide by that new power of 2, which is going to cancel out with that numerator. Thus, it's going to be 1 over 3 squared x to the power of 2. In the third term, the power of 2 will again go up to 3, and when we divide by that new power, we're going to cancel out the numerator. And so this is going to be 1 over 3 cubed times x to the power of 3. Then we can go ahead and integrate the general term. In the general case, you can see increasing the exponent to n plus 1 and then dividing by that new exponent will cancel out the numerator. So what does an integral of the general term look like? Well, it has 1 over 3 to the n times x to the n plus 1, and this continues. We are evaluating this, of course, from 0 to 1. When we plug in 0, all of these terms have an x in them, so they will all go away when we plug in 0. Thus, we just have to plug in x equals 1. I was just writing out what we get when we plug in x equals 1. I'm sorry though, I just noticed an error. Here where I've written 3 to the n, we should have had 3 to the n plus 1. So I'll just go ahead and correct that now. That doesn't really change anything too major. It's just that the nth term of the series has a 3 to the n plus 1. So here where I'm representing the nth term of our series, we should have 3 to the n plus 1 in the denominator. All right, so that is the series representing this integral of our series from 0 to 1, and we've written it by writing 3 non-zero terms, and then we've included a general term as well, which is exactly what the question asked for. And so we are done with part C. And we're in luck. Part D is very easy. We just have to find the sum of the series that we just found in part C. And you probably recognize that the sum we found, this thing, is a geometric series. So to find the sum of the series will be a very easy task. The first term is 1/3. Let's just call this, well, we don't have to call it s. We could just represent it as the integral from 0 to 1, because that's what it is. The integral from 0 to 1 of our function we found is equal to this series, which we can evaluate using the geometric series formula. That's going to be the first term, which was 1/3, divided by 1 minus the common ratio. The common ratio, of course, is 1/3. Each term is 1/3 of the preceding term. 1/3, 1/3 squared, 1/3 cubed, and so on. So 1 minus 1/3. And what is this? Well, 1 is the same as 3/3. So 3/3 minus 1/3 in the denominator, that's 2/3. So this is 1/3 divided by 2/3, and that, of course, is 1/2. Those 3's cancel out, and that is our answer. And that completes our solution to free response question 6 from the 2001 AP Calc BC exam. Let me know in the comments if you have any questions, and please consider supporting Wrath of Math by becoming a channel member to help me produce more quality calculus content. I'll see you tomorrow for the next episode of our Advent calendar.